Okay, looks like we can start. Sorry for this delay. Laptops never work when they have to work. And yeah, first of all, thanks for the sponsor for sponsoring events like this. I think this is much needed. And well, I will go a bit fast. So the idea of this talk is to talk a bit about service mesh. I don't know how many of you may be familiar with the service mesh concept. Has any one of you played with service meshes or read about service mesh? Okay, you may have played with projects like Istio or so. Nice. So the idea that I have in this talk is to explain a bit the core technology that service mesh means. Because if you go to the internet, usually you find, hey, this is Istio, this is the cool features Istio has. You find a tutorial, you know, hey, you can do this thing. But no one is explaining what the hell is service mesh, what is good for. It's just some bunch of cool projects, new technology that is cutting edge, and hey, you have to use that. But no one explains why. And no one explains the new opportunities and why this could be a revolutionary technology when it comes to networking. So I will try to introduce the concepts. Feel free to ask questions during the talk if you want, and also present the different options you have when thinking about service mesh, if you need a service mesh or not, if it's good for you or so. So before starting, let's set a bit of context and see what has brought us to the point where we are to need service mesh or a technology like this. Okay, this is the old story we all know, boring story, how we developed applications in the last 10 years. We had these monoliths that were awesome. Everyone loves the monolith now. No one likes microservices. And the complexity you had when creating applications usually was at most a 3-tier application or something like that, where you had the front end, your web applications, and your backends and your databases. That was pretty simple to deploy, simple to secure. Actually, security was more or less creating a firewall between the front end and the application service, and between the application service and the databases. And that was kind of a model of security by network reachability, right? Which is similar to the model we have today. And we will talk about why this is not good for the modern architectures, okay? Still, we are in Amazon configuring security groups based on IP ranges or other security groups when we want to secure or define who can talk to your instance or to your VPCs. And this is the model we still have today. And this is something that has to change if we want to be able to truly scale to the needs that we have. So these monoliths were simple, but started to grow, and we were adding big features. It became fat monoliths, and there were more complex to redeploy, to patch, to upgrade, and to manage. So many different expertises working on the same code base. It was really, really difficult to maintain. So we started to just break them down into smaller functional areas, okay? The problem is that the patterns repeated in every single small area, and every single small part started also to become more complex. Some of these parts started to have state also, and you have several places or use cases when you had to coordinate transactions, for example, across these different pieces. And one of the things, the most important thing that started to cause trouble is that now, instead of just using the network to reach out to external services, you are using the network to intercommunicate the different parts of your application, right? And that's a big problem because the network became part of the application. And there is a lot of issues on that, okay? You not only need to deal with a typical failure like, hey, this server has crashed or this server has run out of memory, but now we also have the network that is not reliable, and the network fails. It will always fail, and requests will time out, packets will be dropped, and applications have to deal with all that complexity now. In order to fix that, well, when you have failure also, failure in a single service where you have a service chain of say 2, 3, or 15 services, one single failure in one backend service can impact the entire infrastructure. One service starts to respond slow, some requests will time out on the front, and you will not get enough context to understand what's going on. You at most get a 503, the service is unavailable, but in most cases you don't have enough information to understand what's going on. So you need better tools, not only to diagnose your application, but to diagnose what's going on in that network. Most of the tools are very popular, especially the Netflix OSS stack, where you have these service discovery things, the circuit breakers, and a lot of stuff that you can use in your application to just fix this kind of things, right? So if you use a Spring Boot, it's as magical as adding some annotations in there and magic happens and everyone's happy. You have other libraries like gRPC, Armeria for Java, and projects for distributed tracing such as Zipkin or Skywalking to help you understand all the path that a request goes through in a call, in a remote call. Okay? But despite these tools being great and fix the problems, the reality is that all these premises that they provide, the service discovery, fault tolerance, and all that stuff, it's still part of the application. It's still built inside the application. Even if you don't directly code retries or all that logic, it's still part of the application. And that's a problem. Because when you have a big deployment, usually you have a front end that is developed in Node. You have a backend that could be in Java, in Go, in whatever. And that means that all these tools and frameworks and libraries need to be supported in every single language you're using. And not only that, because imagine you have 4 languages and you have this stack. You have to maintain it for 4 languages. Then you release a new version, you need to maintain it for 8. You have the 2 versions to maintain. But not only that, because you cannot assume you can upgrade a fleet of 500 services at once. So you need to release this with backward compatibility. So you need to make sure that each version is compatible with previous versions of every single language. And this combinatorial explosion in the end is kind of unmanageable. Okay? So this is part of the problem of having this logic still in the application, with having network primitives still tied to the application. Okay? So we have reached a level of complexity in the microservices world where many people is saying, perhaps it was wrong going microservices. We should do still monoliths and so on. And for most cases, that's still true. If you are a small startup, have a small project or so, probably a monolith is a good choice. But we have this situation, we have big infrastructures that are dealing with this stuff, and we should have better solutions. Okay? When thinking about these solutions, it's good to think about what we did some time ago. Okay? If we go to the very, very basics, way back when the internet started, we managed to let one single computer send a packet to a computer B, send it over the wire, and even more, it was a super achievement to make it reliable in a way that, hey, service B could respond, hey, I've received the packet, and you were sure that the packet was received. That was kind of a super achievement, and we did that by creating the networking stack. Okay, these are the 2 models, the OSI and TCP, where we modeled every single feature or domain and on a stack basis, so we can build every single layer on top of the bottom ones. Okay, so we have, for example, at the physical layer, when you need to send the 1s and 0s over the wire, there are some algorithms and collision detection stuff that make sure that, hey, you can send the 1s and the 0s over the wire because nothing is going all the other way. It could be crazy to think that in your application logic, you are testing if you can send Ethernet frames out over the wire. No one's gonna do that because it's silly, right? But we are still doing some kind of layer 3 and layer 4 checks, such as these things that we need in microservices at the application layer. So we are dealing with the same kind of problems. Is this service healthy? Has this request reached this service? Because I'm not getting feedback. I don't know. All these primitives are problems that we have already fixed, but we are seeing them in the application layer. This is because it's in the application and the network is coupled with the application in the microservices world. And we need to start decoupling that. We need that kind of layer in the stack just above the application, layer 6.5 or whatever you want to call, that provides all these primitives. So we can just write the applications. And this layer is what we call the service mesh. So the service mesh mainly is there to separate the network from the applications and provide this kind of thin layer that allows you to just focus on the value of the application, not on the network. It also provides consistency along the fleet. Say you have every developer writing their applications. They may use different constraints or conditions to decide if a request has to be retried. Or probably someone before failing says, I will retry 2 times. Some other developer may have hard-coded, oh, I'm retrying 100 times. And then when something fails, why some services retrying, others are not, it's super hard to reason about that. So this service mesh, by pushing these primitives back in the stack, you gain consistency across the fleet. We will see also that we will have centralized control. We'll talk about that later. And also the faster to change. Because all these network primitives, if you want to change this kind of stuff, you don't have to redeploy the applications to affect change on the logic. You upgrade the Netflix library, you have to redeploy your application so it gets the new libraries, and so you don't have to redeploy the applications. You just configure the mesh and push config to affect change. All the service meshes that are out there have 3 main abstractions, which are networking, observability, and security. And these abstractions are the building blocks to build all the functionality that's needed in that layer. Okay. Usually, all this functionality can be just used alone. So if you want to try service mesh, you don't need to adopt the entire thing. Usually, if you want to tackle observability first or get metrics or so, you can just deploy the parts that matter for observability and deal with security later or deal with networking later. Okay. So service meshes provide a progressive way so you can adopt them. Because it's a piece that sits in your infrastructure, and it's pretty complex to update your entire infrastructure to use this completely new thing. Okay, so they have put lots of efforts in making this something that you can adopt progressively. So the most important thing on the service mesh is what we call the data plane. The way service mesh works is what is called the sidecar model. The sidecar model basically is one approach that was started at Google some time ago. Google, by the way, released this Istio project, which is a service mesh project. They were using internally for years, and then they released it. And they started using this sidecar model, which for them scaled very, very well. So the sidecar model consists...
Can I just ask, what's that word you're saying? Is it
sidecar?
How's it spelled?
Sidecar. S-I-D-E-C-R-A-R. Sidecar.
Thank you.
Right. Probably, that's my wrong English probably, but I think it's sidecar. So this sidecar basically is a transparent small proxy that is deployed beside every single service. So for every single service, a small transparent proxy is deployed in front of it. And this is usually automatically done by the mesh solutions. For example, in Istio, which runs on Kubernetes, you just create the deployments the same way you were deploying it always. And there are some webhooks that automatically mutate your deployment and put the sidecar in there. So you get your pod with your containers and the sidecar inside. Okay. Those sidecars intercept all the traffic that goes out of the service and into the service, and they do some fancy stuff. Okay. So, but the idea is that all the traffic that goes out of the service and into the service goes through the sidecar, and then from one sidecar of one service to the next sidecar of the other service. One of the most popular projects for these sidecar proxies is Envoy proxy. It's super cool. It's built by Lyft and heavily developed by Lyft and Google. And it's a proxy that has been built with layer 7 primitives at its core. It's super lightweight, super performant, but you will read a lot of stuff about Envoy that is awesome, but if you want to try, just benchmark it. So when adopting a solution like a mesh, you're putting a proxy in front of every single service, and that always comes at a cost. You will need a bit more RAM, a bit more CPU, and it also will introduce a small latency in all the requests because everything is flowing through the sidecars and the sidecars are processing the requests. So don't trust what you see in the blog post of specific service mesh solutions, just benchmark them, okay? Find what configurations you need about the mesh because sometimes there are many features you can just turn off. Find what you need and benchmark it. Don't trust them. It has also support for layer 7 protocols such as HTTP2, thus gRPC, and it also supports protocols such as HTTP, Mongo, Redis, and MySQL, which means that everything that you can tell these proxies to do, you can use data from those protocols, and we will see how. And one of the most interesting features is the programmability that these proxies have. You can program these proxies at runtime. They have these APIs that they call the XDS APIs that you can use to program the proxies at runtime. Instead of just updating the configuration file, restarting the proxy, and so you can program it at runtime. And it also, these APIs are also push-based and stream-based, so they can be updated live and get information from them live. So once you have this fleet of envoys in front of every single service, you can say that you have a mesh, okay? Because you can program all these proxies to do whatever you want. But it's a bit hard if you have to program, say, 500 envoys. That's kind of a mess, okay? Then that's where the control plane comes into play. A service mesh is the data plane and the control plane. And in the control plane, we find the solutions like Linkerd, Consul, or Istio, which is just a set of high-level APIs where you can just create your configuration, and the control plane will push the configuration to all the envoys. So all the envoys know the state of the mesh and know what they have to do. But you have this centralized control that you apply configuration in one single place, and you can affect the entire fleet, okay?
Sorry, I don't understand the difference between that data plane and...
So the data plane is where the traffic flows, okay? You have these proxies that can be programmed and the traffic flows, but they are kind of silly proxies, okay? They have a set of features that some outlier detection to understand if one service is healthy or unhealthy, and then choose to load balance client side to another one, but they don't know what to do unless you tell them what to do, okay? So this control plane is something that understands the overall status of the mesh. You have the information of every single envoy in there, so you have the whole context to make decisions and what to do. And this programs the entire fleet of envoys.
Okay, so Istio is using envoy?
Yes, yes. You can imagine as Istio as a high-level API, more high-level than Envoy, because Envoy is super low-level, which set some new concepts such as virtual services, destination rules, and so, which are Istio concepts that are translated into Envoy configurations. And they translate these concepts that are more human-readable and so, and push that config to Envoy. So let's see a bit what you can do with this kind of proxies and so. For example, given that all the traffic goes through the proxies, you can easily load balance traffic or just forward traffic based on percentages, or given that Envoy proxies understand layer 7 protocols such as HTTP, you can create routing rules based on HTTP headers, for example. Say you want to do canary deployments. Say, I am rolling out this new version of this service, service V2. I'm going to progressively drive traffic, 10% to version 2, then 30% based on rules, and you can progressively start moving traffic to the new version of the service, unless you can decommission the old one, if it works, and if not, you can just keep traffic going to the old one. You can do that without changing anything, just to applying config in the mesh. Given that it understands also layer 7, you could do also based, for example, on users or groups. Say you have an HTTP with a JOT token after a user has authenticated in a platform, and you can say, hey, just read the group's claim in this token, and if this request comes from QA, from the QA group, just forward the request to that specific subset of services. So you could have the mesh program to say, hey, QA sees this, or development is going to use this environment, and you could do really fancy stuff. Also, just rate limiting requests same way, or just blocking access. A cool thing is that you can also inject failure to really understand how your application behaves when things go wrong. So you could say, hey, for the traffic that comes from developers, just drop 50% of the packets at random. And you can see how your application behaves when things happen. But it's just in the mesh. You don't need to create real failure. You just configure the mesh to, hey, just drop packets for this subset of people. The other important part is observability, which is what helps you understand what's going on, okay? Now, since all the proxies, all the traffic flows through the proxies, you have some premises that you have by default. For example, distributed tracing. Even though for distributed tracing applications still need to do header propagation if you want complete and super meaningful traces, you at least have a trace that for which services the request has flown. And those envoys report the traces for you. Also, they are pushing metrics. Envoy has a lot of metrics, such as requests per second, latency, error rates, and everything. And they are reporting this telemetry data to the control plane. So you can also use that to make decisions. For example, you can create your own dashboards for monitoring your applications based on the metrics that the envoys provide. Even though the developers have not instrumented the applications to provide metrics, you have the metrics for the network that the envoys provide to you. One of the most important things about this thing is consistency. No matter what application, what language, or what team is developing the application, you always get the same metrics. So you can reuse the tools that you have over and over again, which means that if in the future you have a new project or new team developing stuff, you can operate that project the same way because you have a consistent way of monitoring everything. Which also for companies, when you are growing, starting more projects with more customers, and so you can grow your application teams while more steadily growing your operation teams, which saves you a lot of money and a lot of time debugging. Another one is security. Okay, so given that we have the sidecars in place, intercepting all the traffic that's going on, that's a perfect place to put access controls. So this service can talk to this other service. You can also do access controls like this, just by at the data plane. So hey, your service cannot talk here, or you can do fancy stuff like, hey, this service can only talk to this if the request comes from all these paths. Probably if you have, for example, one service that is the one that talks to the storage services, and you only want that to be able to talk to storage if it's, say, for example, a call that comes from development or from production, even though they flow through the same service. It's not just, hey, you can access this. No, you can access this, but under these conditions. You can do things like that based on the understanding of the mesh. And that's a perfect place to apply security policies. And it's as that, you don't need to affect the applications for that, you just change the mesh configuration. But we can go a bit further, and by default, when you have the more services that depend on the network, the more points you can be attacked if an attacker gains access to your network. They can be sniffing traffic or whatever. So we will see that the mesh also provides really, really good primitives to secure communications in your microservices environments by using the identity. So every time a sidecar is started in the mesh issues an identity to that sidecar. An identity, think about the identity about an X509 certificate. So just each sidecar has a certificate for them. So when a sidecar boots, it says, hey mesh, I am here. This is the proof. I prove to you that I'm the service I pretend to be. And then if that proof is okay, the mesh issues a certificate for that sidecar, and that certificate can be used as an identity. Okay, there's a standard that's called SPIFFE that is basically the format of this identity, which basically an X509 certificate with a set of fields. In the SNI or subject alternative name, it encodes this SPIFFE identity. But basically, it's a certificate. Okay, like in your ID card, you have your certificate or so. It's just the same. It's a certificate for every single envoy. With these certificates, you can do cool stuff as having mutual TLS and secure connections by default across all your fleet. So since you have a certificate the same way you connect to a secure website, now you can require that every single service presents a client certificate, otherwise the connection is not allowed. So you have that every single service in your mesh will present a certificate, will validate the other side's certificate, and if those certificates are valid, you can establish a mutual TLS connection. So traffic is encrypted between services. If an attacker gains access to the network, it will not be able to prove to the mesh that, hey, I'm a legit workload here. It will not be issued an identity, and that attacker could not even sniff the traffic because it's all encrypted, but it could not even start a connection to any service in there. Because if the mesh requires mutual TLS, it will not be able to present a certificate and will not be able to even connect there. Okay, so this security model is pretty cool because you have to do nothing. The applications don't need to know. Yeah.
Sorry, your question is in the middle.
Yeah, yes.
How is this different than just use of TLS between HTTP services?
So TLS, that's called simple TLS, where you call an HTTP site, they present your certificate and you say you're okay, but you are not authenticating yourself, right? You are just validating that the server-side certificate is a good one and you trust them, but they are not trusting who you are. In mutual TLS, it's like if you go to the government sites where you need to use your ID card, you are also required to present a certificate yourself as a client. So say, hey, I am this client, and this is the certificate that proves that I'm this client. And this is where the mutual TLS is. The other one is called simple TLS, when just one side presents the certificate. Mutual TLS is when both sides present the certificate, and both sides are authenticated. So any attacker or anyone that's not part of the mesh will not have a proper or valid client certificate, so the connections will not be started. Actually, you can configure the mesh to require mutual TLS or to be permissive, so that if you want to start migrating all the environments and be able to talk to services that are already part of the mesh, you may allow permissive saying, okay, it's okay if someone still does not have a certificate, I'm migrating that stuff, but I want to let them allow to talk here. This is policy that you can configure in the mesh if you require mutual TLS or not. Yeah. So, yeah. But this mutual TLS and encryption is not the only thing that this identity provides, these certificates. More than certificates, so certificates encode one string, that's the SPIFFE identity, that properly designates that service. And that identity is used for stuff that's far, far beyond the security and mutual TLS. This is something that allows you, and we will see how, to break finally this dependency on the layer 3 and 4 that we have. It allows you to apply policies based on the semantics that you care about and to fully leverage multi-cloud and hybrid cloud environments. For example, you can imagine typical environments, well, not such typical, there's no such a thing that people using massively multiple clouds and all the clouds in the world. But for example, imagine that you have stuff in Amazon and also in DigitalOcean, because during development it's much cheaper, okay? And what happens, and you have an on-prem environment with Cube, what happens when you want to connect these environments? So what we do today is, probably if we want the connections to be secure, we configure VPNs, so every single service in those clouds is part of the VPN, and we can route between them in a secure way, and they can talk, okay? The problem is that VPNs are expensive and are hard to scale. Say now that you also need this legacy virtual machine environment that you are migrating to Kubernetes because you are super cool and you want to modernize your infra, and you want that to be part of this thing. You need to also provide the credentials for that VM to join the VPN, or create a new VPN endpoint, or whatever. And that is expensive. This is something that cannot be automated. It's hard to scale. Okay? But if you think about it, a VPN, it's nothing more than traffic that goes out to the internet, but just encrypted using IPsec or whatever. But it's just traffic that goes to the internet encrypted. And the mesh already provides that. If you think about it, so you can leverage the mutual TLS to connect all the clouds that you have. The only thing that you need is one ingress at every single place, the same that you need for VPN. But that ingress, if you think on the mesh, that ingress will have a sidecar. That ingress will have an envoy in there. And that envoy will have a certificate. And all the other components will also have a certificate that have been issued by the same trust domain. Okay? So as long as all these pieces in here can trust the certificates, and as long as you can route something from the virtual machine to the ingress in Google Cloud or whatever, you can just leverage mutual TLS and securely connect between hybrid environments without needing to create VPNs. You don't need VPNs anymore if you are part of the mesh. Even better, you don't need to deal with those IP ranges and so that are imposed by VPNs. The applications don't need to be aware about that. You don't need to deal with certificate creation, because the envoys and the sidecars will ask the mesh for a certificate and that will be issued to them. So the envoys will already have the certificates that can be used to talk to another component. And you don't really care if that is deployed in the same local data center, say, or it's in a completely different cloud, because you are only using the primitives that the mesh gives to you. you're only using that layer of abstraction. Okay? Also, these mutual TLS certificates are cool because they are secure, and the mesh is periodically rotating the certificates. Usually the certificates issues for the sidecar are short-lived, 30 minutes or so they are constantly being rotated to be more secure. So they cannot be spoofed or lived there. Okay. And finally, this is one of the coolest things. If you think about this thing that's identity, the mesh will issue identities for the services. Hey, I am service A, and I claim this thing, and the mesh will issue an identity for that service. But that identity is not tied to a DNS name, is not tied to any IP address, is not tied to anything that's related to the network. It's just something that designates your service as you understand that service in your business, right? And the cool thing about this and all the mesh and the proxies understanding layer 7 protocols is that you can start applying policy based on those identities. When you say, I want this service to be able to talk to this other service, you can just apply these rules based on the identity of that service, not the DNS name, not the IP address. For example, you could say that, and this is food for thought, so this project is Istio, Linkerd, and so don't provide that yet, but the mesh is setting the primitives so this can be done and implemented, and the big companies are working on this unified identity thing. Just imagine that you can have one service in Google Cloud accessing an S3 bucket in Amazon, in AWS, by just authenticating with the mesh identity. Hey, I am this service, this is my identity. Okay, I trust you because you're part of the mesh, and you could access and configure access policies. This guy can access this thing not based on where it's deployed. You don't care if it's a service running on S3, on Google Cloud, or whatever, because you have a unified identity that gives you understanding, okay, this is that service, because it has an identity from the mesh that says, hey, this guy is that service. Even though regardless where the service is deployed, you can have one service deployed in many different regions at the same time for failover or whatever, and you don't care. You apply the policies the same way. Hey, you just talk pure layer 7, purely concepts that are close to your business, to stuff that really matters to you, regardless of where that thing is deployed. And you completely break this dependency on the layer 3 and layer 4 stuff. If you apply the same configuration, just not only for access control, for security policies, but you can also apply that thing for routing between services. I don't care really where the service is deployed. That's the business of the envoys that are underneath. But when I apply policies, I just want to apply them in a way that I can reason about, that is meaningful to me. And where I want to reason about the system, get graphs, and so I can get those metrics. And so based on this information that's super high level, that is what you care about. So this is super cool, and all this service mesh world is going to something like this, where you can finally kind of break this dependency on the layer 3, 4 to apply policies, to apply routing, and depending on IAM roles or stuff that's very, very cloud specific to configure access or so, this mesh will break those boundaries. And today, all these projects that are service meshes are creating the building blocks to make that possible. So just to recap a bit, we have seen that the mesh provides a lot of features for traffic routing, such as service discovery, application level addressing, so you can just talk to service by the identity, not by where the IP addresses they have. You can do these canary deployments, traffic shifting, and all this stuff about routing. For traffic management, you have this outlier detection. You can do client-side load balancing with the envoys, configure retries, fault injection, and all that stuff that helps your application be resilient without having to implement that in the application itself, without coupling the network primitives into the application. Also for observability, you have all the access logs from the envoys, you have all the metrics they provide, that they are huge and super valuable. They give you a lot of insights, and actually the service meshes like Istio come with a set of Grafana dashboards that you can see the metrics, and they are pretty cool. Also the distributed tracing thing and the consistency, you need to be able to scale your projects, your teams, without having to scale every single time your operations. And finally, with security, we have seen that you can enforce policies at runtime. Just on the envoys, you have this trusted identity and this unified identity domain, the mutual TLS, that goes way beyond just securing the network, but allows you to truly have a multi-cloud or hybrid experience with security. Think about not only multi-cloud, but for example, with Kubernetes and VMs. If you want to migrate one legacy environment you have on VMs, with the mesh you can slowly do that. You can just start putting sidecars in front of the VMs, make those legacy environments part of the mesh, and progressively start shifting traffic to your greenfield stuff that you deploy in there. And you can just easily use the mesh, for example, to migrate from legacy. And also authentication and authorization. And as I said, so this is heavily being worked on today. So this unified identity thing is something that people is starting to talk about, but it's not implemented. So people is designing this stuff, how we could implement the lower layers to make that happen in Amazon, in Google, in Kubernetes. And so people is working on that. It's super cool stuff. It's really cutting edge. And it's something that will change how we see networking in the following years. So if you want to take a look at those projects, those are the main ones. These are the links to the different communities that are on these projects with things, well, the typical welcome sites, how to join, how to get involved. And if you want to contribute, those are really cool projects you could be contributing to. And that's it. So if you're awake, thank you. And if you have questions, just happy to answer. Yeah, sure.
I have a couple of questions. First, about the control.
The control plane?
Yes.
Yeah.
I guess you have like a cluster of machines, which are the ones that control the whole mesh or something like that.
Yeah.
Or in that image where you show us the multi-cloud architecture in the mesh, where would you put that, and what address does it have?
Where does the control plane sit in this thing? Okay, so there are different deployment models. Okay, so you can have one single control plane on top of the mesh controlling traffic for everything, and you can have a control plane in each environment. Okay, just dealing with the routing of every single environment. The important thing, for example, for mutual TLS and so, is that the trust domain, the thing that you use to issue identities, is trusted all over the different control planes. So a service mesh can be composed of several control planes if you want. You can federate them, but the important thing for that is the identity is trusted across the fleet. And in the end, it's just about trusting X509 certificates. You can have a root CA and just inherit configuration and so. But there are different architectures. So you can have separate control planes or one control plane that you can deploy wherever you want, but you need access from that control plane to the other parts. Okay.
And the other question is, have you tried the latest Consul service mesh features, and what do you think about them over Istio and this kind of?
I have only tried Istio and Linkerd. Okay. I have not experienced with Consul, sorry, but yeah.
Okay, thanks.
Yep.
101, thanks for the talk. I love the analogy with USC Tower. Now for the question, I see how most service meshes match very well with the architecture of Kubernetes, and actually every single post and blog post and talk I've seen about service mesh uses Kubernetes as an example, because you run your sidecar and that makes it super easy.
Yeah.
Now, is there people running service meshes on like a more say, traditional architecture on AWS? Let's say you have your ELB
VMs,
and your auto-scaling group and so on and so forth. Would you put like, would you deploy your control plane like another application and then put something in before your load balancer?
Yeah.
So that kind of stuff?
Yeah. Actually, my company Tetrade, we are doing a service mesh that's Kubernetes and VMs and so. And that's true that most of the tutorials you will find talk about service mesh like if it was a Kubernetes specific thing, right? Because that's the easy thing. But they give the impression that service mesh is just about Kubernetes. Nothing that I explained today is just about Kubernetes. But also there are efforts in the industry such as the service mesh interface that is being developed, which is kind of building an abstraction for different service meshes so that Linkerd, Istio, and all the meshes can implement the same APIs. But they are building that on top of Kubernetes concepts which is fundamentally wrong. But yes, definitely. So to have a service mesh that expands Kubernetes and VMs, you just have to put the sidecar in there. And the same way that I said that you can have multiple control planes, you can have a control plane just for the VMs in your legacy environment and so, and you can federate the control planes. So actually that's how people is doing this thing. It's installing a dedicated control plane for a mesh in Kubernetes and a dedicated control plane for the mesh in the virtual machine services. Yeah, because the way, for example, of injecting sidecars, configuring the networking so all the traffic from one container flows through the sidecar is different usually than what you will do in VMs. So in Kubernetes, you can do it with init containers configuring IP tables rules, or using the CNI plugins from CNI plugins and APIs, but in VMs it's different. So usually you deploy a different control plane for VMs.
Thank you.
Yeah.
How easy is to test this kind of change?
Sorry?
How easy is to test when you're trying to apply networking rules?
Uh-huh.
Is this environment giving you tools or?
Oh, you mean that to test that what you are trying to do is going to do what you pretend to be doing? Yeah. So by default, all these meshes don't provide this kind of things, but usually you start testing these things since you can kind of constrain where your changes affect. For example, you can say, hey, I'm gonna apply just these routing things, but to a small amount of traffic, or just to this subset of services that are under my control or so, and progressively be applying that. You usually test by rolling out very, very slowly or under a controlled set of services and so. But there's no thing like, I think there's nothing like mocks or something like that. Hey, mock this thing, mock this virtual service and see how it affects traffic or so.
Chaos engineering, you are testing in production.
Yes and no. So yeah, you can test that in production. So usually if you have the staging environment and all that stuff, you first apply all those rules to the staging environment and see how that affects. And then you can roll up the configuration to production. That's the same. So you can apply the same configuration you apply to staging. Okay, this configuration works, I apply it to production. Okay, it's the same. You can also play with failure injection and all that stuff to drop traffic and so, to just make sure that everything works as expected, but it's the same. So you apply the config to your environment, then when you validate that the config works, go there. Cool, thank you.